Hello, everyone. So today we are going to talk about real numbers. So in the previous classes, we have already talked about real numbers, but we do not formally define it. We define it as as the rational numbers plus irrational numbers. But we don't know what rationals. Probably we know what rationals are, like the division of two integers. But what are irrational numbers? So we do not actually know how what number is real and what number is not real. So this class, the main function is to help you find out the real definition of real numbers and accordingly how real numbers are distributed on the real line and some other subset of real numbers like natural numbers, rational numbers, and integers. So it's actually, I'm going to talk about three main axioms. And the first axiom consists of 10 small axioms. The second consists of two small axioms. So there's actually 13 axioms to help to define the real numbers. Okay. And before talking about the first big axiom, we're going to define two operations. So in the last class, we talked about what operations are. And there are two very common operations on real numbers, so sum and product. The sum is for two real numbers a and b, the sum is a, and the sum of a and b is written as a plus b, right? And the product is a times b. So these are two operations. And here we're going to talk about the 10 first axiom, which is called field axiom for the real numbers. The field axiom. Okay. And here is that we in the field in our discussion about field axiom, we first talk about like what is a real number and what is not a real number. So now we already say a and b is a real number, but it doesn't say we know what is a real number. We just say if a and b are real number, then this fact must occur. So actually, this axiom can be written as if a and b are real numbers, then a plus b is equal to b plus a. And this is the commutativity of addition. Okay, so so you can read as if they are real numbers, then this happens. If they are real numbers, then this happens. And if this happens, well, it may not be real number. It might be real number, but it can also be complex number or illusionary numbers. So this is not it's an if relation, but not if and only if relation. So the first two are commutativity and associativity, which we already know, like a plus b equal to b plus a, or the plus, we first calculate a plus b, then plus c is equal to a plus b plus c. And also there's additive identity. So there exists a real number, we call it zero, such that for all real number a plus zero equal to zero plus a equal to a. So this is the additive identity. And also there's a additive inverse, which is for all of the a in the real number set, there exists a b such that a plus b equal to zero. And the additive inverse is defined as if it plus its original number is equal to the identity of the operation. And then the axiom of 5 to 10, of not 5 to 10, 5 to 8, this 4 is same as the sum. It's same as the sum, but it's not associativity of addition, but it's a multiplication. And the logic is the same, like AB equals to BA, AB times C equal to A times BC. So it's actually the same, but the multiplicative in identity is not zero because 0 times something is not equal to something itself, but it's equal to 0, so it's not working. So here, the multiplicative identity is 1. So because like every real number, as you can imagine, times 1 is itself. So 1 is the multiplicative identity. And the multiplicative inverse. This is not for all of the real number, but all of the real number besides 0, because 0 times like x is equal to 1. It's not solvable in real number, because you can say there's x might be very large or infinite, but infinite is not a real number. So, and it's not defined how large x will be. It's not defined. So in this case, we must say without zero, then there exists a b such that a times b equal to 1, equal to the multiplicative identity. And there's also something called a distributive property, which is firstly talk about in set operations. And it's a times b plus c. We can separate the terms out to become ab plus ac. And the last one is called a non-triviality assumption, which is 0 is not equal to 1. And 0, which is the additive inverse, 1 is the multiplicative inverse, and they are not the same. But this one is not able to prove it, so it remains as assumption. And well, we'll see it. We'll see later. So this defined as the operation for addition and multiplication is different. And there's a fact as there's only one number which have the property attributed to 0. So which means the additive additive identity, there's only one number that satisfies it. So if we want to show that, we'll show its uniqueness and its existences. So we know there's a number of 0. So we only need to prove if someone also have the property of 0, they are the same. So suppose there exists a 0, 1, also satisfy 0's property. Then what happened is like 0 plus 0, 1 is equal to 0, 1 plus 0 equal to 0. Because if 0, 1 has 0's property, it plus 0, which is also a real number, and it becomes 0. And also because 0, 1 is also a real number itself, then 0, 1 plus 0 is equal to 0, 1. For 0 has the 0's property. And in the end, we prove like 0, 1 is equal to 0, 1 is equal to this part, right? And this part is equal to 0. So we prove they're the same. So there only exists one 0 has 0's property in the real number set. Okay. And there's another property of 0 is like for all of the real numbers, a times 0 is equal to 0 times a equal to 0. And this will be the second property. And some other fact is like for all of the a, b, which is real number, and if a times b, if a multiplied by b is 0, then it will be very common to think about like whether a is 0, either a is 0 or b is 0. Or yeah, they can be 0 at the same time, but at least a or b is 0. One of them is 0. Okay, so this is another fact. And remember the corollary 4, which is the fourth axiom is the additive inverse axiom. So there is a b such that a plus b equal to 0, and such b has a name. It's called the additive inverse of a, right? And usually we write minus a or negative a because it's natural to think about like minus a plus a equal to 0. So we use minus a usually here. All right. So there only exists one x as a solution for the equation. And this equation is the additive inverse. I remember first we only define the operation of sum, addition, and multiplication, but we can also define another operation called the difference. So what is difference operation? Difference operation is for all of the a, b in the real number, a minus b, we denote it by the minus sign, which is horizontal line usually. And how it defined is defined as a minus b is logically equivalent to a plus the additive inverse of b. So this is how we use the addition and the additive inverse to define the difference or minus operation. And also there's only one number with property attributed to 1. So not only 0, but also 1. And this is from the fact that the for every operation's identity, if it exists, then there's only one, which is from the last lecture. So yeah, the proving method is very similar. So I'm not showing it here, but you can try by yourself to see what will happen. And the corollary of 8, which is the multiplicative inverse, is that for all of the non-zero real numbers, there exists only one y as a solution to the equation at ay equal to 1. Yeah, so ay equal to 1. We denote such y as a negative 1, which is, we'll call it the multiplicative inverse of a. So usually we can write a times the multiplicative inverse is equal to 1. So this is the result showing. Also, there are some other corollaries from the 10 field axiom, the 10 field axiom for real numbers. There are some other corollaries, and let's talk about it. So first, it's like for all of the a, b, which is real number, and b is not zero. This is very important. Then negative of negative a is a. This is our first. This is the first conclusion. The second conclusion is the multiplicative inverse of the multiplicative inverse of b is b. And third is the negative b's multiplicative inverse is minus multiplication. So this part computed first, then take the negative sign. So there are three corollaries, and it's easy to prove them by using the 10 by using the 10 axioms before, and also use some property of 0 and 1. So the third and second example, I'm not showing how the proving process. Will roughly go through the first one, which is the negative of negative a is a. So we prove this. So firstly, 0 equal to 0 is always true because there's only one 0, and minus a times 0 is equal to 1. Minus a times 0 is equal to 0 because everything times 0 is 0. So this is also true, right? So this is if and only if. And all of them is all if and only if, because how we can write 0? We can write 1 plus its additive inverse negative 1. And this one equal to 0. So it goes here to here. And then we can use the distribution property. So we first time this one, and then we time this one to reach this this property. And then we use 1's property. It's like every real number times 1 is itself. So this is negative a, and this is how to write. It's like we take the negative sign in front, so it becomes the negative of a. And because the product is 0, and we remove this item to this side to become a. So they're equal, as is indicated. So every common or very basic ideas of mathematics can be proved using the 13 axioms we're talking about today. And now we learn 10 of them, and then we'll show the remaining 3. Okay, and what's the 11th? The 11th and 12th coming from another axiom called the positivity axiom. The positivity axiom is actually giving so the field axiom, the 10 field axiom gives us a sense like the real number is closed under addition, closed under multiplication, and its basic operation, we can do it. And the positivity axiom give us a sense of the ordering of real numbers, like they can be comparable. Something is smaller than others. This is a very good property of real numbers. So we can compare the size of different members from the real number set. So the real numbers, the positivity axiom says that there exists a subset of R denoted by P called the set of positive numbers, and it has 2 properties. First one is like if a real number A and B are positive, then A plus B and AB are also positive. This means like, I think this should be the B, not B. Okay, so what this implies is that the positive number P is closed under addition and multiplication. So what it means by closed is like when the operation is conducted on the P, and the result is always in P. Because it's always positive, so it's always in P. So this is the first property. And second property is that for all of the real numbers, exactly one of the 3 alternative is true. So given we randomly select a real number, and either this number is positive or is negative, is positive, or is zero. So there's only three conditions. There's no the fourth condition from the real numbers. So this gives us a sense like, well, the the real number is limited. It cannot be something which is not neither positive nor negative nor zero, and that one cannot be a real number. For example, if you say 1 plus 2 times u, this will not be a real number because we don't know this one is negative, non-negative, or it can be something in between. So this is not a real number. Okay, so as we said before, the positive axiom implies the ordering of natural numbers or the real numbers, and for all of the A, B in R. So now we define how we can order in the real numbers. So all of the A and B is real number. Then we define A greater than B. So how we define this term? We may say how we can say like one number is larger than another real number. It's like if we can do its difference, we already define the difference and we compute this difference. We find, oh, it's positive. It's in the set of P. Then we define A is larger than B. And commonly there's also smaller than, greater or equal to, smaller or equal to, and they are all coming from this fact. So greater or equal to means like if A greater than B or A equal to B. So this means like first we define greater than B, so we can use greater than B and equal to B to represent the situation of A greater or equal to B. So what is smaller than B? A smaller than B implies. This implies like B is larger than A, right? A smaller than B, so B is larger than A. So it's just taking the inverse of this one. And we just replace B here and A here. So this one is also defined. And smaller or equal to, well, we just taken B to be here and A to be here, and we define it. So all of the how we can compare equal, larger, smaller, equal, or larger, equal, or smaller, the 5 comparison, we all have defined it. And if we ever see an equal sign, it means there's an equation like A equal to B plus C. But if we see something like A smaller than B minus C, then this is an inequality. So in every like expression, there's a small, larger, smaller, equal to, larger, or equal to sign occur, and it's called inequality. Okay. And we'll talk about some properties of inequalities. It's like the first one is like the square of any real number, which is not equal to zero, is a positive number. So not equal to zero is important because zero squared is zero, which is not a positive, it's zero. But if it's not zero, then it's greater than zero. So the square is always a non-negative number. Okay, so one example is like 1 not equal to 0. Now we can prove the non-triviality assumption because 1, remember like 1 square is equal to 1, right? 1 times 1 is 1 square, which is 1. Why? Because 1 times every natural number is itself. So 1 times 1 is 1. And because 1 is not 0, right? 1 is not 0 because there's only 1 0, and 1 square is equal to 1. So 1 square is larger than 0, and 1 is larger than 0 as a result. The second property is like if a positive number A is positive, then its multiplicative inverse is also positive. So this can be think as like 2 over 1 times x equal to 1, then x is 2. Because if this becomes a negative number, then they're well, for example, negative 2, then they will emerge a single negative sign, which will turn into negative 1, which is not what we want, right? And the third and fourth property is like if A greater than B, C greater than 0, then AC greater than BC. If A greater than B, C smaller than 0, then AC smaller than BC. So for all of the positive numbers, and the inequality times another positive number, it will not change the sign's direction. But the direction is changed when we apply both sides with the same negative number, so it will change the sign during the operation. And we can also define the interval, like for all of the AB, the real number AB, A is smaller than B. And because if A is larger than B or equal to B, then, well, what is AB becomes A smaller than X smaller than A, which is an empty set, which is not very meaningful in real cases. So A smaller than B, we can define the following intervals, like AB with open both sides. So each time you see this bracket, it means an open interval, which means the endpoint is not included. But if you see this or this is open, and this one is closed. This is closed. So AB with open interval is A smaller than X smaller than B for all X. And the closed one side, which side is closed is becomes like smaller or equal to. And if both closed, then it's smaller than equal to X, A smaller than equal to X, and B greater or equal to X for all X in the real numbers. And we have talked about a lot of finite, infinite, and negative infinite terms when we studied the cardinality. And now we can use a symbol to define those terms. So infinite is this side. It's a 8, which is lying down. And the negative infinite is a negative infinite sign. So very easy to understand. But notice that infinite and negative infinite is not real number. So they are not in the set of real numbers. But this one is equal to real number, which means like all of the numbers between negative infinite and infinite is in R. So why this is true? Because it's a open interval, so itself is not contained in R. All right. And with these two signs, we can define some more intervals like a negative from negative infinite to B, both open interval, and it becomes like all of the X in R, X smaller than B. And you can never write something like that, like there's negative infinite and B. And this makes no sense because this one is not in the real number. And this set is actually becomes like well, maybe we'll simplify it as right in this form. So what this set implies is R union with the set of negative infinity. So this is beyond real numbers definition. Okay, and so this is so now we talk about what is open and closed interval by a informal definition. And we'll do a formal definition of closed and open interval in the probably in the next lecture or the next one. All right. And in the fourth lecture, we talk about mathematical induction. And now we want to define a new set called the inductive set. Inductive set is defined as with two properties. So a set S of real number is an inductive set if the number 1 is in set S. And if X is a member of S, then X plus 1 is also a member of S. So you can always think about the inductive set as 1 plus something in it. And also, like if 1 is in it, 2 is in it, because 1 plus 1 is 2, and 2 plus 1 is 3, and it becomes that. Very similar to a natural number, but it doesn't mean it cannot contain negative 1. Negative 1 can also be in it because it also satisfies these two properties. We can also add some square root of 2 to it, and it doesn't affect. It's still an inductive set, right? So inductive set can be a real number, the whole real number set, but it can also be pretty small, like a natural number set. So the formal definition of a natural number is not, we say it's 1, 2, 3, 4, 5, but it's defined as the set of the intersection of all inductive sets. So remember, the intersection of all inductive sets is also the smallest inductive set. So it only contains one and each terms plus the previous term, 2, 3, 4. So this will be the smallest intersection of all inductive sets. And it is very pure without any zero in it, because if zero in it, it is not in the intersection of all inductive set, because 1, 2, 3, 4, 5, 6 to infinite is an inductive set, but it's not included in it, right? So this is how we define natural numbers formally. And the fact is that if A is a set, it's a subset of N, is a subset of natural number. And if A is inductive, then A is the set of natural numbers. So why is that? Because natural numbers is already an intersection of all inductive sets. So it's the smallest. So any proper subset of N is not inductive because it's even smaller. So if A is inductive, it must be itself, or it will be a proper subset of natural numbers, right? So there's two very important properties of N. It's also called the closure of N under something, like natural number is closed under addition and multiplication operation. So the property of natural number is this two. And the proof process of the plus and multiplication is very similar, but we'll do one proof of the multiplication and the addition, which is even easier, and you can practice by yourself to see whether it works. And yeah, the main logic we use is mathematical induction. So first we do the base case, right? We do the base case, and if n is equal to 1, and m times n is m times 1, which is m itself, which is also in n because like mn m and n is in natural number, so their result is also in n. So we prove it. And the inductive cases, we first suppose mb is in the set of natural numbers. So mb, yeah. So this is our assumption, and we want to show b plus 1 is also in it. But n times b plus 1 is equal to, using the distribution property, we divide the two terms out, and these terms is in it. And m times 1, well, m times 1 is what? M times 1 is m itself. It becomes this one, right? So they are also in it. Then if we can do the, how you say, if we can do this one, which is the addition form version, we call it addition form. If we can do this one, and well, we plus these two, and they're also in the set of natural numbers. So it's proved. So one is proved, and the mathematical induction works by the base case and inductive case. Okay, so now we have already defined natural numbers, and next we move to the second set, which is called the set of integer. So the set of integer is consisting of all natural numbers, the number 0, and all negatives of natural numbers, and it's denoted by z. So what this means, like, we can write it as z is equal to n, right? And but also union with the element 0, the number 0, also with negation of all of the elements in it. So this is not the negative of the set. We cannot define negation of a set, but it's like, this means like all of the negative of all natural numbers. We can mean this one here. Okay, so this is integer, seems larger than the natural number, but we know their cardinality is still the same. Okay, and the property of z is very similar to the property of n, which is like the addition, the difference, and multiplication is also in z. So there's only one difference, m minus n. This can also be integer, but if m and n, they are natural numbers, m minus n might be not in it. for example, n is equal to 1, n is equal to 5, then minus equal to -4, which doesn't belong to the set of natural number. This is because, so we can say, well, the difference is not closed under the operation of like the natural number is not closed under the operation of difference. Yeah. And the third set we're talking about is rational number. So rational number is the set of quotient of integers in the form of m equal to a divides b, with ab belongs to set of integers and b is not equal to 0. So there's three things happening here. So first, m is a quotient of two integers. Oh, well, yeah, the first thing is like m is a quotient of two number a and b. Second, a and b are integer. Third, b is not equal to 0. And if these three things satisfied, then m is definitely a rational number. And we denote it by q because it always represent the quotient, right? And the quotient we talked about in the last lecture when we talking about divisions. And the property of the rational number can be more complex than integers. So first one is like the rational number satisfy the field axiom. So it's no longer like it is closed under addition and multiplication. It has more property. It has all of the 10 properties here. So which means like for all AB in rationals, we can change all of this R's into Q, and they all of them holds for here, like A plus B equal to B plus A. So yeah, those 10 properties are of the rational numbers. Okay, and the second property is like if Q is equal to B A divided by B with AB equal to Z, AB belongs to Z and B not 0, then A or B is odd, which means like imagining there's a Q belongs to a rational number and Q can be equal written as not A divided by B, but like N M divided by N, then M odd. If so, we want to prove like if n is odd, then if n is not odd, then n is odd. Okay, so why is that? Imagine we are so first we'll do the contradiction one. So assume like both of them not one of them is odd. So both of them are even, like 10 divided by maybe 12, right? So both of them even. And this can be simplified. It can be simplified into 5 divided by 6. So we can, because if both of them are even numbers, then they can also divide it by a factor of 2. Both the numerator and denominator, both the m and n can be divided by 2 and to form another simpler form. And maybe 5, if I'm imagining like it's also taken from like 20 over 24 divided by 2 equal to that form. So we will continue the process until we get at least one of them is odd. So they will not contain, both of them contain the factor of 2. And this is what we try to do here. Okay. And there's a theorem. And this theorem is important as the beginning of real analysis. So the theorem is called there's no rational number whose square equal to 2. So yeah, it gives us an inspiration that rational number is not all real numbers, and this is found in the history of math as a significant point that humans at first time know there are some numbers that cannot be represented by rational because in ancient world rational number seems contain everything, but this theorem shows that it doesn't contain every number in reality because the square root of 2 is not rational. So how can we do that? We'll do that by a proof of contradiction. So first, suppose there exists one x belongs to rational number such that x squared is equal to 2. Then x is equal to a divided by b. So this is a direct result. And by the properties of rational numbers above, a or b is odd. So with a b belongs to z, b is non-zero, and either a or b is odd, right? Either a or b is odd, and this is a very important point for now, and we'll keep it denoted as 1. So in this case, x squared, because x squared is 2, so x can be written as a divided by b. So a squared divided by b squared is equal to 2, and a squared equals to 2b squared. So a squared is even because it has a factor of 2. And probably from the last example of the first lecture, we proved that any integer with a square form even is also even, right? We proved that by a contradiction, by a proof by contradiction strategy as well. So if a squared is even, a is also even. And so we can write a as a is equal to 2k, right? Because it's even, so k is an integer and a equal to 2k. And a squared is equal to 4k squared. So b squared, remember b squared is equal to a squared divided by 2. So if this divided by 2, it will be 2k squared. So what happened here is b squared is also even, so b is even. So both a and b are even, which means, well, it's contradict to the property 1. Either a or b is odd if x is in the set of rational numbers, right? So this one gives us the final contradiction. So the number whose square is 2, or x squared is 2, x is not a rational number. Cool. So after someone showing that in the history of math, and the human knows like we cannot develop real number system only with rationals, or equations like x squared minus 2 equal to 0 is not solvable. Because yeah, x squared minus 2 equal to 0 has some real meanings, like for example, this parabola, this point is -2, right? And this is x squared minus 2. And the solution equal to 0, it has two solutions. So how can we find it? By using the rational number, you cannot define this 2 point. It remains as a question mark, but it actually exists in real world. So, or the right triangle with 1 and 1. How we know this one? It's root square of 2, but it's not rational number. How can we write about this number? There's some question emerged when people prove that the rational number cannot denote the root square of 2. So it seems like besides the field axiom and positivity axiom, we need an additional axiom to ensure that there exists an x belongs to R such that x squared is equal to 2. And we denote that idea as our last axiom, the 13th axiom, called completeness axiom in the end. So before talking about completeness axiom, we first talk about what's some definitions leading us to that place. So first one is the upper bound. So we say for any non-empty set S of real numbers, and it's said to be bounded above if there exists a C belongs to R such that for all of the elements, the members of S, the non-empty S, is smaller or equal to C. So this set S is bounded above. And such number C is called upper bound for set S. So we can do visualization of that. So, well, this is real number, and this is C. This is S. Well, so this set is S. And it's, well, the largest element here is still smaller or equal to C. C is here. Well, so it's a C is upper bound, is an upper bound for set S. And namely, like because it's upper bound, it's visualized as, well, beyond this point, x, there's a boundary of x not exceeding this point, right? This is the like the graphical explanation. And also why we need why it says, well, it's the empty set of S. What about set S is empty? If set of S is empty, then there's no point of X. S, what is S? It's not happening here. So, well, is this upper bound? We don't know because X is not a curve. So this one, yeah, it's actually bounded by S, right? Because it's satisfied, like for all of the element in S, this statement is already false, so it's worse. But it has no meaning because S is not exist. So logically it's true, but it doesn't have real meanings in mathematics. Okay, so because if C is the upper bound for non-empty set S, all numbers larger than C are not S upper bound. So yeah, are all S upper bound. So imagining this again, and here is S. This is C, like I would say, like all of the elements smaller than C, smaller or equal as in the same case. Then what about the point here? If there is a point greater than C, and they are all upper bound of S. So there are infinitely many upper bound for S. Is if we can find one, then we just found a greater number to say it's also an upper bound of S. And this is by the fact that there are infinitely many real numbers. It's an infinite set. So now we define the completeness axiom. So the completeness axiom for the real numbers indicates that if S is a non-empty set of real numbers that is bounded above, as the number C exists in previous cases, then what happens in the set of all upper bounds for S, there exists a smallest or least upper bound. We can see like that. We can see they are all S, and there's some upper bound here, and these are all upper bound. We say Ci, and we can always find the C0 here. This is the least upper bound, the smallest upper bound among all of the upper bound of S, and this can be found. And the existence of the least upper bound is the central of the completeness axiom, and the square root of 2 or square root of C for all C in the positive number set can be found by the completeness axiom. So this is how the completeness axiom is used. It's used to find the such very interesting number, we call it irrational numbers. So the completeness axiom is applied besides the range of rationals to include the irrational numbers also in the real number system. Okay. And yeah, it has a name because they're very important. Such a least upper bound or smallest upper bound of S is called the supranom of S, which we call sup S. And there's some strategy to prove a number is a supranom of S. And we'll talk about what's the common strategy. So first, we want to show some number is the least upper bound of S. First is upper bound, right? So we will first show such a number is an upper bound. Yeah, very direct. And first and second, once the number is the upper bound, so we'll also show that such number is less than any other upper bound for us. So yeah, this is to say, like, once we found a number C here, yeah, it's an upper bound. And here is also another C. And we want to find, this is S, yeah. And the second one is like, we found such C is less than any other upper bound. So for the set of all upper bound, this is smallest. And this is also to say, for all of the, number that is smaller than C, Like this is smaller than C, right? This is smaller than C, and they are not upper bound for S. We can also prove it in that way. And another strategy to say for all of the number smaller than C, there exists another member of X, which is larger than Ci for all of the I here, right? So that's the third way to prove it. And this why is the most direct. And we can find, like, we fix the C. I'm going to show, like, for all of the Ci smaller than C, there exists one X belong to the set S that's greater than Ci. Then we say, well, this is the most non-direct ways to prove a number is the sup S. All right. And the completeness axiom is important to build up the real number system, assisting to mathematical analysis. One good example is it guarantees that uh, there exists one x in the real number system such that x squared is equal to 2. And such x, we define it as a rational number because so how irrational number is defined is very informal. Usually it doesn't have a formal definition of what's irrational. It's always like irrational number defined as R minus set of Q, and what remains is the irrational number. But this is a pretty large set. When you study the measure theory, probably at the end of this course, we'll see that the cardinality of irrational number is much greater than Q, and it's the same as R. It's same as the real number. Okay, so this theorem is also very important. This is the central theorem of today. I think it's called, like, when we can fix a positive number C, then there exists of only one x in a positive number such that the equation of x squared equal to s to C has a unique solution. All right. So this is a general version of the square root of 2 example. Because we can say that when we say root square of 2 square is equal to C is equal to, oh no, wait. So now we can say, like, we want to prove like x squared equal to 2 have only one solution, have only one solution when x is greater than 0, right? There exists only one. Satisfied. And now in this case, 2 is no longer 2. It's for any of the positive number. It can be 3, can be 2.5, and maybe it can be root square 2 itself. And you also have another number that is square equal to it. Okay, so we're going to prove this important theorem. So first we can define set. We can define set called S. And now S becomes all of the real numbers such that x is greater or equal to 0 and its square smaller than C. And then we will apply the completeness axiom. Because C is greater than 0, then S is non-empty because at least 0 is in it. And as C becomes larger, the set S becomes larger. And because a non-empty set, then for all x, for all of the x inside it, is square smaller than C. So x is smaller than root square of C, right? Even we don't know what that is, but we can denote that x is smaller than some value, so S is bounded above. So by the completeness axiom, because S is non-empty and bounded above, there exists a least upper bound. So we use the B to denote the least upper bound here. So in this case, X S here, and here is B, the least upper bound. Now, because B is larger than C, because, well, C is okay. So now what we're doing is, like, we suppose the situation happens like B squared is greater than C. Like B is not C. Then what happens, like, there exists R such that B minus R is greater than root square of C. And this is from the fact that it's from here. X smaller than it. And when b is larger than c, then b squared minus like r squared, which is also positive and is larger than c, right? And so maybe, yeah, this can be true because b squared larger than c, then b larger than root square of c. Taking the root square, still the same. But this one, if we written this way, it will becomes like, it will become, well, if this is root square of c, then this form is become like b squared minus r squared, root square of that. Well, it's not equal to this one. So the more clear and wise way is to written this way. And there exists a r in it, which use the Archimedean property. We'll talk about later, and we'll find this one is true, right? Okay. And in this case, what happened is like b minus r is also an upper bound for s because, well, because all of the b minus r is greater than that one, and x is smaller than the root square of c. So b squared, b minus r is also upper bound for s. And in that case, b is not a least upper bound of s because b minus r is smaller than it. R is if we choose r equal to b minus root square of c, well, in this case, if we choose that, if we select this one, and obviously b is larger than root square of c, and this is positive, right? And we select that, we'll find out b minus r, b minus r is larger than b minus this one, which is, yeah, so this makes sense. Yeah, so the contradiction occurs. We first assume b is a least upper bound. We define it in that way. But if b squared is larger than c, then yeah, then it's not, then b becomes a upper bound. It's not the least upper bound. So yeah. So b squared must be smaller or equal to c. And now we will prove in another direction. We'll suppose b is smaller than c. Then we can also choose r equal to root square of c minus b because once by the definition of smaller than, then b squared smaller than c is equal to c greater than b squared, and which means like c minus b squared is uh is larger than 0, right? And also the root square minus b is also larger than 0. And we can define this one. What we can define this one? We can define this one. Let me think about. We can define this as something called q. And because q larger than 0, there exists a r between q and 0 by Archimedean property. So this is how we define r here. So r is greater than 0, and r is also smaller than root square of c minus b. Then we find out like b plus r is more than c, the root square of c. And because b plus r is in the set of S, and b plus r is larger than b, right? Then b is not a least upper bound. Because, well, this is because like there exists a smaller element of b. There exists a larger element of S that is in the set of S, and it's larger than b, so b is not the upper bound. There exists an element beyond b. Well, so it's also a contradiction. So in this fact, with one, we can find out it must be the case that b squared is equal to c, or b is equal to the root square of c. So this is our final conclusion. So the least upper bound for S, for this set must be the only one number, b, and is equal to root square of c. And this is exactly the solution for S squared equal to C, which is B. So can find the solution for this. For this equation is B equal to root square of C. So we prove that we can find solution for such equation, but it's just like it's a real number. It's just not rational numbers. It's a irrational number. Okay, cool. And there's also a number called the lower bound. So a empty set as a real number is said to be bounded below. Very similar. There exists a B in the set of R, such that for all x in S, B is smaller or equal to x. So very similar to it. So this is x, this is x, this is set S, and there's a B here, and it's smaller than all x. Right? This is lower bound. And such number B is called a lower bound for set S, and such set S is bounded below. And it can be a infinitely many lower bound for all of that number smaller than B, right? And if such bound exists, there's a greatest lower bound that is like closest cuts through the set S. And this may be called B0, the greatest lower bound. And we always call it the infimum of S. And this one, we call it the infimum of S, defined as the inf S. But here, inf is not infinite, it's the infimum. This is the greatest lower bound definition. Okay. And we'll talk about another fact is the theorem of like for a non-empty set S that is bounded below, there's a unique infimum of S. So this is very similar to the completeness axiom, as we said for non-empty set S. There, if it's bounded above, then there's a unique least upper bound, and there exists a unique greatest lower bound inf S. And we can prove it, not prove it very long. We can prove it shortly with only two facts: the completeness axiom and also the by defining a new set T, and T is defined in reflexive of the set S respect to 0. So T is defined as all of the x in real numbers, but all of the negatives of x in S. So here, like this one is T and this one is X, they are reflexive by the point 0. Okay. Thus, for all of the X in the set R, B smaller than equal to X, it also means like negative B is larger or equal to minus X. And this is by the property of inequality, because we times a negative 1, which is negative number, and it turns to a different direction. Okay, so what next? What next is like B is a lower bound for S, likely here, maybe here is a negative. We may say B is a B is the lower bound for S, and then negative B here is the upper bound for T. That makes sense. And by assumption, S is bounded below. So S is bounded below, so such B exists. So T is bounded above, right? And by the completeness axiom, there exists only one. There is only one sup T, which is the supremum of T, the least upper bound of T. There exists only one that, and we know it by C. And then by the reflective property, then there's only exists one negative of C, such that the infimum of S, the infimum of S is minus C, and for the non-empty set S, and this is how we prove it. Yeah. And as a result, the real number is defined as the set of numbers that satisfy simultaneously the field axiom, the positivity axiom, and the completeness axiom. and such a set is defined as the real numbers, defined as R. So by using if a number that satisfy, if you check them one by one, that you find out, well, it satisfy all of the 13 axioms, then we can say it's a real number. But such process can be very lengthy or very long if you do the 13 properties one by one and compare to check each pair. So it is a definition, but it is not a criterion for you to decide if a number is a real number. It will waste most of the time, but by fact, if you see a number that in your life, it will be a real number. That's my wise way to define what a real number is. So yeah, which way you like is better is all fun. But yeah, today just introduce like 1 hour way to prove some number is a real number. Okay, and there's some properties about the real numbers. I think I will talk about it maybe in the next lecture. So the next lecture will not be will not be talking about sequence as it is supposed to be, but we'll talk about more fact like triangular inequality, the density of different set of real numbers. So yeah, so probably that will be the next class schedule.